And last, before the tea break, we've got Rory from SRK.
How do I compete with a presentation like that? Thanks, Ray. Um, all right, so my presentation is going to go back to basics. I think there's a fundamental need for the understanding of InSAR, its fundamentals, and primarily its limitations. So, introduction. This was really recently stated to me by a senior engineer. I don't trust InSAR because I don't understand the results or its limitations. It's a very justifiable comment, especially when you hold a position of responsibility or liability on an engineering project, whether it's open pit operations, civil operations, tailings dams, and the engineers cannot divorce themselves from design accountability. So they need a comprehensive understanding of the monitoring techniques from the basic principles to the interpretation of the results, all the way through the process chain. So they need to understand what the system is, what its functionality is, what the measurements are, and its limitations. Right, so what is InSAR? This was covered by Glenn yesterday. Synthetic Aperture Radar. It's a remote sensing technique that uses echo-coherent radio systems from satellites orbiting the Earth. It records amplitude and the phase of each acquisition, each satellite pass. And on multiple acquisitions, you can start to stack these images, geolocate, geoprocess them, and you can start to work out changes in the SAR images behavior, whether you're dealing with backscatter results, the functionality of moist soils or vegetation. But more importantly, in today's context, it's primarily used for deformation monitoring. Relative, not absolute. But what it does is it's looking at the length of the phase, the wave, and changes along that. But we'll get to that just now. So where is it typically used? As I said, primarily used in deformation modeling nowadays, substance modeling. It's becoming more commonly used in geohazard identification for slope stability, for landslides, glacier tracking, volcanoes. You can start to track their movements and start to predict potential eruptions. Infrastructure, we've used it for road monitoring, sinkhole detection. We've used it for tracking aquifers, recharge and discharge in Saudi Arabia. It's got an ever-increasing application throughout the industry. It's becoming a lot more used, a lot more commercially viable, and it's been implemented a lot more. So a lot of you are going to stumble on this. If you haven't yet, you very likely are in the future. And it's good to understand the basics. So back to basics. Right, so why is it important? It's becoming a very key part in a lot of legislative compliance. GISTM was talked about a lot yesterday on the tailings dams. There's a requirement for a lot more comprehensive monitoring on large-scale human development projects. There's a lot of accountability, not only to the developers themselves, the mining operations, but also on a civic and moral sense. You want to prevent these potential failures, hazard avoidance to protect loss of life and associated causalities from there. So there's a very strong mandate internationally for comprehensive monitoring standards, although InSAR isn't necessarily dictated in those compliance manifests. It's becoming a lot more widely used because there's a lot more satellites going up in space. It's becoming a lot more accessible. You're going to come across it, and it's a very good tool in a comprehensive toolbox. So what happens when it goes wrong? Who's liable? So on the top left-hand side, that is New South Wales. That is Cedar Dam, I think, or Acacia Dam. And thankfully, they had very comprehensive monitoring systems on that site. Disaster was averted. There was no loss of life. It was a success story. However, on the right-hand side, you've got, it wasn't Brennadero, sorry, I have a look at my notes, Fundeo tailings dam disaster. There was a loss of 19 lives in this year, 2025. Catastrophic. People are held liable, and this is one of the big things with monitoring. You've got extensive accessibility to different monitoring solutions. Multiple people are held liable, and you need to justify when things went wrong. How could you have prevented it? What actions could have been taken to avoid any potential knock-on effects. So liability, that's going to be one of the key words that comes out of today. So there's benefits though. So InSAR has very large spatial coverage. When we're processing InSAR data, Sentinel-1, for example, you want typically 750 by 750 pixels as your minimum dimensions. That correlates into a 15 by 15 kilometer area. Bare minimum. You can cover entire provinces if you start to stack, synthesize, and geo-merge your data sets together. But you're covering a lot more spatial area than you would with any ground-based terrestrial monitoring. Terrestrial monitoring it's difficult. Tailings dams, for example, they have odd geometries. It becomes expensive. So although this is a very capable system, remember it's relative deformation. Don't be looking at absolutes, but it targets you into areas of anomalies that you can start to then focus your other monitoring capabilities or your other infrastructure onto more critical areas. But from this, one key takeaway is one size does not fit all. One processing algorithm does not handle, from civil engineers to roads, sinkholes, through to slope stabilities. But the bottom one is you can monitor through cloud cover. This is a huge advantage of InSAR. So it's not limited in that aspect. What's happening in recent years? You can see on the right-hand side, 2024-5, there's a lot more satellites that are coming online. As I said, it's becoming a lot more commercially available. The resolution is increasing. You're getting down to 0.25 meter resolution, and it's going to hit a frequency of 2 to 4 hour repeat time global coverage on some satellite providers. So there's a lot more focus on this. It's becoming very accessible. Data overload? No, sort of. But it's not becoming something we can ignore in the industry. Thought I'd put this one out. Right, okay, but there's other band combinations. So you use fit-for-purpose band combinations. X-band, great for civil applications if you're looking for very finite measurement monitoring, deformations. Unfortunately, it's not very good in vegetated areas. So as soon as you start to go from XCS L band, you go into 23 centimeter wavelength, and you're able to start penetrating vegetation, denser vegetations. So you can see what's going on behind there. Unfortunately, when you get to the longer wavelengths, you lose that resolution on the deformation profiles. All right, limitations. So let's start with roles and accountability. As we talked earlier, it's a very key factor in this industry. One very key service provider, InSAR service provider, said, we shall not be held liable for any processing, use, or interpretation of the data by the user or third parties. Basically, you paid a huge amount of money, they've given you a data set, and they walk away and say, cheers, thanks, bye-bye. We had a case in the DRC with a big dump that they were monitoring, and it failed. The client went back and said, where were the precursors? Why wasn't this alerting us? Well, there should have been something. And the methodology that they applied wasn't correct in this instance. And they turned to this and said, cheers, sorry, thanks, bye-bye. You can't do that in the industry. The end user, at the end of the day, the engineer of record and people like that, they're held accountable by all these data sources. So accountability is key. The end user needs to be asking these guys, hold on, if you're now stepping away from this, where do we start falling, in the legal spectrum? So that talks to who are the key players in this. You've got the geoscientists, a lot of us that are going to be processing this data. There's a lot more freeware software that we were talking about earlier, where one click, you're getting pretty results, pretty pictures. But do you understand what's actually going into that data? Do you understand what the limitations are? You need to be held accountable for it. It has to be traceable. You have to have auditable workflows. So every time you do an iteration, you need to make sure that it doesn't matter what system you're using, whether it's a commercial system or your freeware, it needs to be trackable, because at the end of the day, the lawyers are going to come to you and say, justify yourself. And with changing data sets, changing dependencies and Python code and all the rest of it, if you don't stay on top of that, if you don't actually know what's going on behind the scenes, you can find yourself in a very deep legal quagmire. And then end user accountability. At the end of the day, they need to make the informed decisions based on your data sets. So they need to have confidence in your data sets. So where do we start? I mean, there's 100 different parameters on each of the different processing methodologies. This isn't, the aim of this talk. Let's start back to basics. So choose your band. X band, 2.3 centimeter wavelength through to L band, 23. Ask your service provider which one is more applicable. Everyone seems to be selling Terasar X. It's expensive. They make good money off of it, but you have to ask those questions. Is it fit for purpose? What's the processing technique? There's an array of different processing techniques from, persistent scatter, distributed scatter through to SBAS. SBAS is more like a flexible tape ruler where it's approximating over a couple of points and looking for key trends, but it includes a lot more coherence loss, a lot more error. Persistent scatter looking for very coherent targets. So which is most applicable to your site? And should you be using multiple approaches to justify, validate your data? We like looking at enhanced SBAS. So you're looking at PS, you're looking at SBAS, and you're looking at DS, and you're assimilating all those data sets to try get a comprehensive package. Parameters. What goes in? These are commercially, sorry, not commercially. These are open source data sets available on the internet. Four out of 5 of those look great. So, people, they just download, put it in their software, but they haven't actually validated the data. They haven't, checked the integrity of the data. So when you start to look into it, ALOS, this is an area in Namibia. As soon as you start to apply a hill scan coloration to the data set, it looks terrible. And as soon as your SAR process is starting to vector normalize your results, it's going to give you erroneous results if you're looking at larger areas. But if you start to question the integrity of the data, suddenly this one looks a lot more applicable. You can get more reliable data sets out of the input parameters. What other key parameters? I mean, it sounds logical. Where if you're looking at the right hand side of your pit, you sort of want a satellite on the left hand side, but not everyone interrogates this. Often people say, okay, well, I'm just going to buy said satellite platform. We're only going to buy one. We've got a pit that's 600 meters deep. It doesn't mean it's fit for purpose. Maybe you need multiple acquisitions. If you've got multiple acquisitions, then you can start to geocompose it into 3D vectors to get a more holistic image of what's actually happening. But these are key questions that not just the geoscientists that are producing this data set, but also the end user needs to ask. They need to be aware of this. Validations and checks. So the black box approach, with a lot of the commercial software packages, or sorry, the service providers, they'll give you a result. It's a pretty DEM. Maybe they'll give you a time series, but they're not telling you what the coherence is. They're not telling you what the mu sigma is. The reliability, repeatability of the results. The confidence in the results, and it can lead to your loss of confidence, but it can also lead to legal quagmires further down the road. So don't be afraid to ask what's actually going into your data sets and run parallel. If you need to use, an external consultant that runs very similar workflows that, can parallel process to validate your data, don't be afraid to use that. Quality control checks are absolutely paramount, especially when you've got access to multiple monitoring systems. So if you've got prisms, TDRs, ground-based radars, use those to validate your InSAR results. You shouldn't be using a single source, a single monitoring source for broad site stability, safety considerations, legal compliance, things like that. All right. The other key one is trends. How do you visualize your data? Now, whether you've got a GeoTIFF, whether you've got PS data, there's a lot more information behind these that people aren't able to interpret. So what sort of tools do you have available, even as an end user? There's a lot of freeware commercial packages. I mean, you could be using QGIS, for example, for some of your visualization. You can be writing Python scripts for looking at some of your trend analyses and looking for anomalies. you need to be more cognizant of what's in the industry. Now, a lot of the people we run into, they don't know how to ask the questions. They don't know how to approach the questions. I think this came up yesterday on what are the correct questions to ask. Geophysicists should actually be approaching the clients and saying, this is what's best practice for you. This is what you need. So tell them, if you've got a preferred solution that's, adequate for data visualization, for finding anomalies, relay that to them. There's no industry standard. There's never going to be. Everyone's got their own little commercial hold on things. Software companies, they what do you call it? You've got pay licensing and things like that. But it shouldn't stop end users from being able to interrogate their data extensively. Only recently has one of the big satellite producers actually started to allow you to download the data to interrogate. Before they only had, sorry, now I removed the page, but they only had online portals where you could interrogate their data and start to look for trends, and it was very limiting. But once you start getting your data, what do you start doing with it? Are you informed as to look for inverse velocity relationships? Do you know that you're starting to predict, potential time of failure if you've got certain linear or certain trends? What does the coherence tell you? What if you've got coherence loss? Does that correlate to water on the ground? Do you have water seepage in one of your walls? Or it could be something very simple as someone just grading, an area of your road. Understanding these principles is absolutely paramount in the industry. It's often overlooked, and it's unfortunate. A lot of people say they get too busy or they got too many balls to juggle. But at the end of the day, it's all about legal compliance. And as an engineer of record, or even as a geoscientist producing the data, you need to make informed decisions based on the data sets available. And you can only do that if you've actually got knowledge on how the interpretation should work. And if you don't, please contact people that do. But you shouldn't, as I said earlier, you shouldn't use it as a standalone. I mean, as Glenn said yesterday, you should be stacking your data. You should be looking at multiple data sets sources. In this case, we just ran a couple of Sentinel-2 detections over a random site to compare that to InSAR. Are we starting to see variations, trends, correlations between the InSAR deformation to environmental anomalies? But the data is becoming a lot more dense. You have a lot more bands. I mean, Firefly has over 120 bands. You were talking about over 220 bands yesterday. So down to 1.5 meter resolution once you do pan sharpening. It's exceptionally sharp, but it doesn't. This is expensive data. It doesn't mean you should be limited to only the expensive data. There are freeware data sets out there that the informed end user should start forming as the initial baseline for interpretation of their results. Why are there anomalous trends? Has the geoscientist actually processed it correctly? The geoscientist should be comparing the InSAR results to other viable data sets. This is available. Not every site has ground penetrating radar or ground terrestrial radars or prisms, but amalgamation, comprehension of those multiple data sets is absolutely paramount. I mean, this was a simple one. This automatically got filtered, but in this case, we had a lot of cloud cover. Cloud cover relates to water. Water related to an anomalous point in the InSAR data set for that point. It's easy to cross-correlate. So even the end user should be able to verify these sorts of results. But then came to the visualization that I talked to earlier. No linear stretch. You're not going to see any anomalies in that data set. So you need to start applying graphical interpretations, stretching, quantizations, bilateral adjustments to start looking for anomalies. Now, an anomaly doesn't mean that you've automatically got a failure. It means it's an area that you need to investigate further. You can start getting trends. You can start to, predict off of those. But again, it's supposed to highlight you into areas of concern. And then, as Glenn did yesterday, where you start to hyperstack everything, because I know you're going to ask questions. So, as I said, integration from multiple sources, it's absolutely paramount. There are software solutions at the moment that do that. James was talking about it yesterday, where the implementation of informed decisions from multiple data sets is paramount. But there are solutions on the market. So do look around, do ask around. Don't, look at InSAR and say, I don't fully understand it. We need to now walk away from it because it's not going anywhere. And then we start to stack it. So now that you've got the repeatability of the InSAR scans, that is going to come down to about 2 hours, you can start to treat it like terrestrial radars, and you can actually start to set proper trigger thresholds in the future. But you need to have the correct understanding of your interpretation. You need your geoscientists, your engineers to tell you what the soil profiles are, the domaining, geotechnical domaining. Look at the historical trends and start to make future predictions. Right, I did say it was back to basics. I do apologize. But yeah, it shouldn't be a single monitoring source. It should be used in parallel with multiple monitoring solutions. So hopefully that was back to basics. Got tweaked a little bit of interest, but you need to be asking the right questions to your consultants, to your geoscientists. But as an end user, you can't just wipe your hands and walk away from it. It's not going anywhere.
Thank you very much. Questions? Glenn.
Not Glenn.
It was a compliment, not a question.
Not Stephanie, not Glenn.
I actually loved the presentation, but I'm a bit biased because, of course, I work in the same space. It's just two comments, The first one is there's two large mining companies. I won't mention their names. And they say that their data is being processed by a company in Spain. And it's InSAR data. Why don't we have people who are offering services to these mining companies? Are we too expensive locally to a point that South African large mining companies rely on Spain for monitoring? The second aspect of it is, and this is not only meant for you, for everyone here, I deal with a number of mining companies as part of my role, but I don't see those who are signatories that you have mentioned there in the room. So it's like us as service providers, we're actually preaching to each other. And my question is, where do people learn this if not in part of conferences and so forth? So it's not only just for you, but for everyone else. But the first one, at least you can try to comment on that.
So the first one is you're probably going to talk about companies like Trialtimira or the likes. We're not going to say GeoApp. But they've got a very good market hold because they started a while ago. And as I said, there are large commercial companies that, although they've been doing this for a long time, they weren't always using the correct algorithms, as was proven in the case in the DRC. There was a very large dump failure, astronomical, and there was no trends. The other thing is they're processing the data, as I brought up earlier, in black box solutions. So they process it, they give it to the end user. When you actually start to interrogate the data, and I'm pretty sure I know one of the clients you were looking at with that, but look at the data spacing. So TerraSAR X, you're going down to a 3-meter resolution. Look at the pixels on the output results that they give you. It's 15 to 20 meters. And the client doesn't know how to critique this. So the geoscientists, sorry, let's go to the end users, such as the engineer on record, needs to have a better understanding, especially as this has been implemented a lot more, on saying, well, we paid for 3, why do I have 20? What have we lost in between? Have you started to do the flex board, like SBAS, where that point might be moving a lot, but the other two aren't? So have we lost that resolution? Have you applied the correct processing methodology? They'll say SqueezeR and things like that improves the resolution. How? Prove it. Run parallel process. It's not that we're not doing it in the industry. We are doing it. We do it, but we do a lot of back analysis. So this also ties into your second question is, people generally come out of the fold when something goes wrong. So when something goes wrong, they're going to have meetings and say, oh, well, what should we have done? Who's actually liable? Then the guys are all sitting around the table. When it comes to information like this, the engineer on record or the geotechnical engineer, they need to have an understanding of this. And it's becoming a lot more prominent in the industry. They can't step away from it. Everyone knows InSAR.
Same. I cannot see any of them attend conferences. We always get called whenever these crises, but not that interesting.
It's the problem with delegation. So they will get, a junior engineer to look at the data and they'll set triggers. Every now and again, they'll get an external consultant and say, okay, well, what do we set our trigger thresholds to? Which is great. You need to have those triggers, but they need to be calibrated, at least annually, typically 2, 3 times a year to set those thresholds. Those are typically done on your ground-based radar, and then that should correlate through to your InSAR monitoring. Delegation is a problem, but the biggest problem with that is accountability flows upwards. Talk to them.
Can I ask one last question before we go to tea? I was picking your brain over lunch. So I had a student who's looked at a year's worth, just trying to think, about once a month for a year's data over the Geophys tailings dam. And I was like, oh, we're going to publish this data. And then after this conference, I'm petrified to publish it because you mentioned, and also you mentioned as well, just not saying anything. I know you're not allowed to say anything about Geophys. And I mean, we were using free software. We didn't interrogate the data that much. I mean, you've really challenged me to go back. I mean, we looked at the coherence, but not the mu sigma. Is it a wise thing to publish something like that to make people aware that it seems there was a signal ahead of time? I mean, or there's just too much risk that we might get sued for something, or like...
If you're going to publish, you're going to have to be fully informed.
Okay.
Like I said earlier, it's right there in orange. You can't treat InSAR as a single standalone monitoring system. So you need to have a comprehensive knowledge of what your geology is doing, what your ground conditions were, rain factors. There's a lot that goes into that. So high-level publishing is always very dangerous, from a